You have learned about discrete random variables and some special distributions. We are now ready to move on to continuous random variables. Consider a dataset consisting of weights in grams of human male brains. We can visualize these data with a relative frequency histogram. Here, class intervals are chosen so that each rectangle represents a relatively large number of weights. Weight, however, is a continuous random variable. Recall that this means that it can take on any value within some interval. Another way of thinking about that is that weight must be measured as opposed to counted. Suppose now that the sample of weights was very large, possibly consisting of hundreds of thousands. Because weight is continuous, there would be a reasonably large number for each rectangle, even for small class intervals. When such small classes have enough observations in them, it becomes possible to stop thinking of the histogram as a collection of rectangles and instead approximate it by a curve. The curve used to describe the distribution of this variable is called a probability density curve. The probability density curve tells what proportion of the data falls within a given interval. One special type of continuous distribution is a uniform random variable. A uniform random variable is used in scenarios in which a certain characteristic is spread out evenly across a given medium, such as area or population. Examples include: the distribution of mitochondria in a cell may be uniform, indicating consistent energy production capacity throughout the cell's volume. The distribution of hair follicles in the skin of an animal may be uniform. A certain plant species may be uniformly distributed in a forest, which may indicate that the species has roughly the same access to light, water, or other resources. The probability density function of a uniform random variable y is as follows, though we will use R commands to find uniform probabilities. If y is a uniform random variable with parameters a and b, then the mean can be shown to be mu sub y equals the quantity a plus b over 2. And the standard deviation can be shown to be sigma sub y equals the square root of the quantity b minus a squared over 12. Now one note about R commands. You've seen commands such as dbinom, pbinom, and qbinom. The command that begins with d corresponds to the probability at an exact value. Though we will use these with discrete random variables, when we have a continuous random variable, this probability always equals 0, because there is no area under a single point in a probability density curve. So, with continuous random variables, we will only use commands starting with p to find cumulative probabilities or q to find percentiles. Alright, let's jump into an example. In each acre of a forest, the number of a certain species of shrub is uniformly distributed between 1,000 and 4,000. Suppose that an acre of the forest is randomly selected. What is the probability that fewer than 1,600 of this type of shrub are found? We will model this scenario with a uniform random variable y with parameters 1,000 and 4,000. The R command that we will use is punif, with x, a, and b as inputs. This command finds the probability that y is less than x when the parameters of the distribution are a and b. Let's go ahead and define a to be 1,000 and b to be 4,000. To find the probability that fewer than 1,600 shrubs are found, we compute punif 1,600, a, b. We find the probability to be 0.2. Note that with a uniform distribution, probabilities of events correspond to areas of rectangles. What is the probability that the number of this type of shrub is between 1,600 and 3,000? Here our strategy will be to first find the area corresponding to the event that y is less than 3,000. Then we will subtract the area corresponding to the event that y is less than 1,600. We have punif 3,000, a, b minus punif 1,600, a, b, which yields a probability of 0.4667. What is the mean number of shrubs per acre? The mean is given by the quantity a plus b over 2, which equals 2,500. What is the first quartile of the number of shrubs per acre? The QUnif percentile, A, B command returns the given percentile. The first quartile is equivalent to the 25th percentile. We find the first quartile to be 1,750. Consider another example. It may be beneficial to pause the video and try this on your own. Human hair grows from the scalp in groupings known as follicular units. The number of follicular units per square inch is uniformly distributed between 420 and 550. In a randomly selected individual, find the following. What is the probability that the number of follicular units per square inch is greater than 500? Would it be unusual if the number of follicular units per square inch is between 520 and 530? What is the mean number of follicular units per square inch? Suppose that hair in the top 10% is considered dense. What is the cutoff for this standard? Okay, let's define A to be 420 and B to be 550. We want to know the probability that the number of follicular units per square inch is greater than 500. Recall that the maximum here is 550, so we run punif 550, A, B minus punif 500, A, B to get a probability of 0.3846. Would it be unusual if the number of follicular units per square inch is between 520 and 530? We find this probability to be 0.0769, which is not a particularly unusual event. It happens about 8% of the time. What is the mean number of follicular units per square inch? The mean is given by the quantity A plus B over 2, which equals 485. Suppose that hair in the top 10% is considered dense. What is the cutoff for this standard? We need to find the 90th percentile here. We find it to be 537. Okay, let's move on to normal random variables. A normal random variable is used in scenarios in which a certain characteristic is continuous and symmetric around a central value. Biological examples of the normal distribution include modeling continuous physical traits such as body size, cholesterol levels, or enzyme activity. Modeling the distribution of drug concentrations in the bloodstream after administration. Modeling allele frequencies within a population. Modeling the distribution of disease incidence within a population. Here we have the probability density function for a normal random variable y with parameters mu and sigma. You can see it's a rather complicated formula, but again we will use R commands to find these probabilities. Note that the mean, mu, and the standard deviation sigma are parameters of the normal distribution. We have to know these in order to find any corresponding probabilities. And the shape of the distribution changes depending on the values of mu and sigma. Let's take a look at how changing mu and sigma affects the shape. Let's consider an example. A study investigating maternal investment in a frog species found that Y, the volume of egg clutches measured across 11 study sites, had an approximately normal distribution with mu equal 882.5 and sigma equal 380 cubic millimeters. What is the probability of observing an egg clutch with volume between 600 and 800 cubic millimeters? Let's start off by defining m, the mean, to be 882.5, and s, the standard deviation, to be 380. We will use the R command pnorm x, mean, st to find the cumulative probability less than x. We have pnorm 800, m, s minus pnorm 600, m, s. The probability that the volume will be between 600 and 800 is 0.1854. Would it be unusual for an egg clutch to have a volume greater than 1,550 cubic millimeters? When dealing with greater than probabilities, we first find the corresponding less than probability, and then subtract that from 1. We have 1 minus pnorm 1,550, m, s, which equals 0.0395. It would be unusual to find an egg clutch with that much volume. What proportion of egg clutches had volume less than 400 cubic millimeters? We use the pnorm 400, m, s command to find that the proportion is about 0.1021, or 10.21%. What is the size of the smallest 5% of egg clutches? We find the 5th percentile using the qnorm command. We find it to be 257.46. Let's consider one additional example. Try pausing the video and working this one on your own first. Hemoglobin A1C is often used as a marker of compliance among insulin-dependent diabetic patients. Suppose that among diabetics who comply with taking their insulin shots, that A1C is normally distributed with mean 8 and standard deviation 2.5. What proportion of compliant patients have A1C less than 7? Okay, so let's define M, the mean, to be 8, and S, the standard deviation, to be 2.5. The proportion of patients with A1C less than 7 is given by pnorm 7, m, s, which is 0.3446. A diabetic patient comes to a clinic with A1C of 12.3. Is it likely that the patient is not complying with their insulin shots? Well, the probability that a patient will have A1C of 12.3 or more is given by 1 minus pnorm 12.3, m, s, which is 0.0427. This is considered to be an unusual event. It seems likely that the patient is probably not complying with their insulin regimen. What is the range of A1C values for those considered compliant with their shots, using the standard that those in the middle 80% of the distribution are compliant? Let's start by taking a look at the distribution with the middle 80% shaded. We can see that the unshaded area is then 20%, with 10% being in each tail. From here, we can see that the lower boundary of the shaded area is the 10th percentile, and the upper boundary is the 90th percentile. The lower range of A1C values for compliant patients is qnorm 0.10, m, s, which equals 4.8. Here we're rounding to the nearest tenth. The upper range of values is qnorm 0.90, m, s, which equals 11.2. Okay, so that's it for the content for this lesson, but it's a good opportunity to learn a little more about R. Let's talk about how to define a custom function. Suppose that we wanted to create a function that computes the probability that y is between a and b when we know that y is normally distributed with mean mu and sigma. First, we need a name for our function. How about we call it normprob.ab? We make the assignment and use the function command to indicate that we're defining a new function. We need to put all necessary parameters inside parentheses separated by commas. Then we open a curly bracket. All commands in our function will go between the open and closed curly brackets. To find the probability that y is between a and b, we need pnorm b, mu, sigma minus pnorm a, mu, sigma. Don't forget to close the curly brackets. And now we have a new function that we can use. Recall the example where the volume of frog egg clutches had a normal distribution with mean 882.5 and standard deviation 380. Let's again find the probability of observing an egg clutch with volume between 600 and 800 cubic millimeters. We're going to use our normprob.ab command. We enter normprob.ab 600, 800, 882.5, 380. We find our probability is 0.1854. Now we could stop there, but I'm going to make our function just a little bit fancier. Let's have it print out the sentence, the probability is, and then we'll fill in the probability. The cat command, which is short for concatenate, allows you to combine different things into the same line. In our function, I'm going to call the output from our calculation C. Then I'll include the line cat and then the string the probability is, C. Let's rerun our function to see the result. Okay, here's one for you to try. Suppose that we want to know the lower and upper values that bound a given middle area, A, of a normal distribution with mean mu and standard deviation sigma. Note that the trick here will be to determine how much area is in each tail. This area is 1/2 times the quantity 1 minus A. Pause the video and give it a shot. Now there are different ways to go about this, but here's how I do it. I'll check it by reworking the last question from the A1C example where y is normally distributed with mean 8 and standard deviation 2.5. We were looking for the values that bound the middle 80%. Running my function, I get 4.8 and 11.2, which agree with the earlier answers. So that's it for this video. You really need to make sure that you're comfortable with continuous distributions, in particular the normal distribution. We're going to be using this one a lot in the next lesson and throughout the remainder of the course.